We introduce video see-through mixed reality with focus cues. Conventional head-worn displays suffer from the vergence accommodation conflict, which causes blurry vision and eye strain due to inconsistent vergence and focus distances. Solutions in mixed reality exist for optical see-through displays. However, these solutions inherit the problems of optical see-through displays, including a limited field of view, lack of proper occlusion of physical objects, as well as poor color and contrast reproduction. We introduce the first video see-through display for mixed reality with focus cues, which enables high-quality coherent renderings. In order to deliver high resolution within a compact form factor, we design gaze-contingent layered displays that can adjust the focal distance of all layers based on real-time measurements of the user's vergence distance. Our approach combines the advantages of both varifocal and layered displays and thereby can deliver high-quality focus cues over a large workspace, even when the precision and accuracy of eye tracking is limited. This allows us to use a minimal number of physical display panels to cover a large workspace. To enable fast focusing, we use an electrically adjustable liquid lens for capturing the real environment and for adjusting the focal distance of display panels. We build a two-layer display prototype which consists of two 2.9-inch LCD panels per eye, each with a resolution of 1440 pixels square, 4 tunable liquid lenses from Optitune, and two 200Hz eye-tracking cameras from Pupil Labs. We compare gaze-contingent layered displays against a conventional varifocal display by gradually varying the error that is introduced by the eye tracker. We introduce mixed reality focal stacks, an efficient representation of mixed reality content that lends itself to fast processing for driving layered displays in real time. Mixed reality focal stacks build a complete end-to-end pipeline for capturing, rendering, and displaying mixed reality focus cues that uses only off-the-shelf hardware and compute components. We make use of layered displays to enable unconstrained focusing within the volume defined by the display planes. We capture a focal stack using an off-the-shelf video camera and a focus tunable lens. To ensure high video frame rates, we continuously change the focal power of the lens. We compensate for motion within a captured focal stack by synthesizing the remaining images of the focal stack based on the current and previously captured images. Stacking images with objects in motion results in ghosting artifacts, which are most prominent on the edges of the moving objects. We reduce motion in focal stacks by shifting pixels so that the objects in previous frames align with the objects in the current frame. We use a signal generator to drive the lens with a step function and to trigger the camera. During focal changes, the beam moves in image space and therefore appears as a line in the captured image. We adjust the offset between the point in time where the signal is sent and the point in time where the shutter is opened until the beam stops moving during exposure. We make use of a layered scene representation, which we fill with multi-view information. Subsequently, we dilate the edges of occluded areas to compensate for missing information. We process the MPI from back to front while computing the contribution from each of its layers to all focal stack images before we progress to the next layer. We sort the circles of confusion that will appear in a layer in order to reuse pixels from a smaller circle in a larger circle of confusion. We combine the rendered with a captured focal stack image by augmenting the captured image with the rendering. If scene depth is available, we resolve occlusions using depth sorting, thus augmenting rendered pixels only where they occlude captured pixels. We compare our approach against a conventional varifocal display in a controlled test environment. The user is focusing on a moving plane, while the system estimates the vergence distance. Due to erroneous eye tracking data, the estimated vergence distance differs from the actual distance to the target plane. Notice how our design is able to diminish the error